If we ask the same questions here, which you ask your students, what will be the results about Big Bang? Yeah, good. We should do it.
That's a good question. I have no idea how well science is taught in high school classrooms here. Is it very effective science education?
But don't forget, we don't have such a gap between the religious point of view and scientific.
That's a big difference.
Yeah, that's the difference between Europe and Russia from one side and America from the other side.
Yeah. Big difference.
Thank you very much.
Спасибо. Thank you very much.
Сейчас я приглашаю Дэвида Кристиана. У нас остались сравнительные истории гуманоидов как живое выступление, и затем еще одно видеообращение. Напомню, что Дэвид является президентом Международной ассоциации всемирной истории, собственно говоря, автором концепции универсальной истории, членом Австралийской академии гуманитарных наук, общества естественных гуманитарных наук Голландии. Как говорится, это все о нем. That's all about him.
Thank you very much. Я очень рад быть здесь. I would like to thank the organizers for inviting me and my colleagues. It's a great privilege to be here. This is the last talk of a long day. I hope it will be not too serious. It's about space invaders, but there is a serious point behind it all. My title is Comparative Humanoid Histories, and I'll explain what I mean by that as I go. You, by the way, are here. This is a fantastic picture of Saturn taken looking back towards the Earth. Big history. Craig has talked very eloquently about big history. Big history looks at human history in a cosmological context. And because of that, it can help us think about the future of our species. It's a powerful tool for thinking about the future. As big history has emerged, another discipline, astrobiology, has emerged from being science fiction to becoming a really serious science. The science is evolving so rapidly. And astrobiology, too, I believe, may help us think about our nature as a species and perhaps about our future as a species. So here's the question I would like to look at. Are we alone in the universe? Could we contact other humanoid species? Could we perhaps imagine a future university in which there were courses called comparative humanoid histories? And if so, what would these courses tell us about our own species? So here is the handbook for a future university. It's advertising a new course, History 100, Comparative Humanoid Histories. And this course will compare and contrast the histories of different humanoid civilizations in various star systems. It will focus on how and when humanoid civilizations appear and how successful they are at surviving for long periods of time. I want to see if I can guess what the contents of that course might look like. Today, we can do this more seriously than we could have 50 years ago. We have a lot more evidence and we have a lot more theories. There's a lot of guesswork, but we can now think reasonably seriously about such questions. So how rare are human-like or humanoid species? How lucky are you and I to be born as humanoids? If you're born into this universe, what are the chances of being born as a human being or a human-like creature rather than as a mote of dust or a meteorite or a cockroach? This is the question that the Buddha asked over 2,000 years ago. And I'd like to begin with his wonderful answer. He said to his disciples, in the beautiful, lilting language of the Buddhist sutras, "Imagine, O disciples, that the whole earth was covered with water, and that someone were to throw a yoke with a hole in it into the water. Now suppose that once in 100 years, a blind turtle were to rise to the surface. What would be the chances of the turtle putting its head through the hole in the yoke? And his loyal disciples said, "It is very unlikely, O Lord." And the Buddha replied, "It is just as unlikely that one will be born as a human being." That's the Buddha's answer 200 years ago. Today, we ask a similar question: what is the chance of contacting other humanoids? And the astrobiologists who pose this question often use a version of what's known as the Drake equation. It was devised by an American astronomer, Frank Drake, in the 1960s. It looks like an equation, but it's really a series of questions. Here's a very early version of the Drake equation, but I'm going to use a simplified modern version. Let me explain it briefly. N is the number of humanoid species that exist right now in our galaxy. Now, I do have some modesty. I'm not going to talk about the whole universe. I'm simply going to talk about one galaxy. So what's the number of humanoid species existing right now? Now, here's the equation. N stars is the number of stars in our galaxy, times the fraction of planets, of stars with planets, times the fraction of planets that have life on them, times the fraction of living planets that have humanoids on them, times the number that actually exist now. So let me take you through a modern version of the Drake equation. I'm sure you've seen different versions of it. The Drake equation today, it's still based largely on guesswork. I don't make strong claims for this, but we know a lot more than Frank Drake did, so we can perhaps give some slightly better answers. Okay, let's begin. N stars, an estimate of the number of stars in the Milky Way, perhaps 400 billion. Now, 400 billion is a lot of stars. Let me give you a feeling for this. If you count 1 and 2 and 3, one number each second, to 1 million, it will take you, I don't know if you want to guess, it'll take you a little over 11 days. That's counting 24 hours a day. Now, if you count to 1 billion, it will take you 1,000 times as long, which is about 32 years. If you count 400 billion, that will take you about 13,000 years, which is more time than has passed since the last ice age. That's a lot of stars. Now, how many of these stars may have planets? Well, here we know a lot more than Frank Drake did, because in the last 15 years, we have learned to detect planets around nearby stars. And the Kepler satellite, launched in 2009, is looking for stars in our region of the galaxy, and it's finding hundreds and hundreds of them. So we have evidence now that planetary systems are very common. In January 2012, I came across an article suggesting that there may be more planets than stars. So an average of about 1.6 planets for every star. Realistically, 1 or 2 planets per star, that means there may be 400 or 800 billion planets in our galaxy. So here's our equation counter. So let's estimate that there's 1 planet for every star. That's conservative. That would mean there may be 400 billion planets in our galaxy. Now, what fraction of them may have life? How many are life-friendly? Well, recently, it's beginning to look as if a majority of these planets are rocky, small rocky planets. Initially, we just found large gassy planets, but we're finding more and more rocky planets, comparable in size to the Earth. Here are just some pictures, artists' recreations of some of these recent finds. Now, how many of these planets may be life-friendly? What does it mean to be friendly to life? Well, you need to be rocky, you need to be chemically complex. There needs to be lots of chemicals. You need to have stable orbits, not too erratic. You need surface water in liquid form. Complex chemistry is almost impossible in gases or solids. So you need a planet whose temperature has stayed within the narrow range that allows water to exist in liquid form. Water really is the key to life. So how many planets might be life-friendly? Well, we're guessing. In our own solar system, 3 planets and several moons may have been life-friendly at one time, but only one is known to be life-friendly. So I'm going to make a wild guess at this point that 10% of planets may be life-friendly. That would mean there are 40 billion life-friendly planets in our galaxy. But how many of them actually have life? Well, we know more than Frank Drake did here too. On our Earth, we know that bacterial life appeared almost as soon as the planet was cool enough for life to appear, about 3.8 billion years ago. And what this suggests is that on a life-friendly planet, life is very likely to appear. But what we're talking about, of course, is bacteria, very simple bacteria. And this means that there may be 40 billion living planets in our galaxy. Bacterial life is very common. But who wants to talk with bacteria? What fraction of planets may have humanoids? Now it gets more complicated. First, what do we mean by humanoids? In the original Frank Drake equation, he had a term that was F-intelligence. He equated humanoids with intelligence. Now, I think this is a mistake, a serious mistake. Dogs and cats are intelligent, but they do not do the things that we do. The technologies of humanoids, such as the capacity to emit radio signals, are not produced just by intelligent species. There are many intelligent species on this planet. They are produced by intelligent species that have such a powerful system of communication that they can share information with each other and accumulate information from generation to generation, so that information and technologies build up without limit, and they build up faster and faster. So I'm going to suggest a definition of humanoid species. Humanoid species, it doesn't matter what they look like. They could look like octopi, but they are capable of collective learning, of building technologies. And this definition will turn out to be useful. Okay, how many planets evolve humanoids? Humanoids are much rarer than bacteria. There are many evolutionary steps between bacteria and humanoids. On our Earth, it took almost 4 billion years. That's almost a third of the age of the universe to evolve the first humanoids, us. So you need a planet that remains life-friendly for billions of years, and that's difficult. Both Venus and Mars may have been life-friendly once, but they both ceased to be life-friendly for different reasons. So, once again, I'm going to take a wild guess here. And I'm going to guess that humanoids evolve on 1 in every 1,000 living planets. If that's true, it would mean there have been 40 million humanoid species in our galaxy. So here's our next equation counter. 40 million humanoid species may have evolved over 10 billion years. Now, how many exist right now? That's the final term in our equation. To estimate that, we need some idea of how long humanoid species survive. We need to do that course in comparative humanoid histories. But I think that my definition of species driven by collective learning will be helpful here. So let me suggest what humanoid histories may look like. We imagine a species capable of collective learning. It's probably the first species on its planet. Its first stage is childhood. Technology slowly built up. On our planet, they built up over 100,000 years. And they build up faster and faster because some technologies speed up the process of exchanging ideas, such as writing or the invention of printing. People share learning. Technologies build up. They become more and more powerful, their populations grow, they consume more resources, until eventually the pace of technological change becomes so fast that they enter a second stage. Stage 2 is adolescence. Change is now very fast. They invent new forms of energy. On our Earth, fossil fuels, increasing control of energy, the invention of nuclear weapons, rapid population growth, radio technology. Radio technology is important because it means we become visible to other humanoid species if they exist. We can see all sorts of evidence of this accelerating trend. We can see it in human population growth over 100,000 years. Here's a graph showing this. We can see it in consumption of energy, a staggering increase in per capita consumption of energy, mostly in the last 200 years, so that now each of us on average consumes 100 times the energy we need to survive. We're even messing up nearby space. We're filling it with space debris. There are tens of millions of small particles moving at 28,000 kilometers an hour. Very dangerous for spacecraft. The Swiss are very clean. The Swiss are planning to build a satellite that will clean up this space debris, by the way. So here we have a picture of an adolescent humanoid species that's flexing its technological muscles. It's entered stage 2 of its history, and now it's looking for other humanoid species. And it's become dangerous. When J.R. Oppenheimer, scientific director of the Manhattan Project, witnessed the first nuclear test in July 1945, he was reminded of the words of the god Vishnu, "I am become death, the destroyer of worlds." So stage 2 marks a dangerous crisis for all humanoid species. If they're capable of collective learning, eventually they will become a planet-changing species. They will have increasing control of energy, rapid population growth, dangerously high consumption of resources, and probably something equivalent to nuclear weapons. They will be capable of destroying their planet. This we can think of as the bottleneck. There's a wonderful post-World War II science fiction novel called A Canticle for Leibowitz. It begins in a Dark Age world, after a nuclear war, the flame deluge. Slowly, science is rediscovered in this world. Eventually, people learn to make nuclear weapons again, and once again, they use them. This is a picture of a species that keeps throwing itself back into the Dark Ages. So, is stage 2 a stage in which all humanoid species destroy themselves? Do no humanoid species get past stage 2? If so, humanoid species are like galactic fireflies. They flicker in and out of existence. And our chances of encountering other humanoids are very limited. You can estimate that if, on average, a humanoid species survives for 200 years after entering stage 2, then there are only 1 or 2 humanoid species in the entire galaxy at any one time. We won't encounter them. We won't even know how tragically similar our histories were. But that's pretty pessimistic. And perhaps it's too pessimistic. Let's hope it is. Perhaps collective learning makes humanoids so clever that they can find a clever route through the problems of stage 2 and enter a 3rd stage in their history. The 3rd stage is maturity and sustainability. How do you get to stage 3? Of course, I don't need to say we are in stage 2, so this is the question we all face. Well, this is the main challenge for all humanoid species anywhere in the galaxy. To meet it, you have to do 2 things. It's like driving along a road and encountering a terrible traffic accident. You have to see the problem, and then you have to swerve to avoid it. Big history can help with both these challenges. It can help us see the dangers because it provides the cosmological perspective we need to see the dangers clearly. It can also help us avoid those dangers because it provides the global perspective that humans will need to collaborate globally to solve these problems. So can we steer our creativity into new directions? It's a central question for this Congress. In my lifetime, we've begun to see the problems and to see them very clearly. When I was a child, we didn't see them. Now we see them very clearly. That's promising. Can we steer global society away from the obese, high-consumption technologies of stage 2 towards technologies that can build a better life for all without overconsumption of resources. There are hopeful signs. Population growth is slowing down. We're building less obese technologies. This is wonderful. This is a little pump made up of a single molecule, 1/1000th of a meter long. It spins 50 times a second around a single sulfur atom. It could be used to pump blood through the cells. Here's another example of nanotechnology. Can we do this? We'll also need to rethink what we mean by growth. We cannot work with a definition of growth that implies ever-increasing consumption. We have to change our ideas of growth from consumption to well-being. So we have to think very carefully about what we mean by a good life. Beyond a certain level of wealth, well-being, a good life, does not depend on more consumption. It's compatible with sustainability. So, back to the Drake equation. If humans reach stage 3, they will survive much longer, so the chances of meeting other humanoid species are greatly increased. You can estimate that if a humanoid species survives for 200,000 years after entering stage 3, there may be at any time 1,000 to 2,000 other humanoid species in the galaxy. So our chances of meeting them increase very significantly indeed. This is a way of thinking about our future. None of my specific conclusions should be taken too seriously, but I think thinking about these questions may help us think about our future. This 3-stage model of humanoid histories may be a very helpful way of thinking about human history: beginnings, crisis, maturity. And today's challenge is one all humanoids face. Can we get to stage 3? I thank you for your attention.
David, thank you so much.